Yeah.
Okay.
Am I audible now? Can anyone please confirm?
Yeah, it is audible.
Okay. Thank you. So, welcome to live session 7. So, today what we will do, um, in live session 7, we will discuss upon welding and joining of non-metals. So, non-metals in the sense, mostly it will be plastic welding, or else it can be some glass welding or kind of ceramic welding, or in some sense plastic to metal welding also. So there are also different means except whatever we have discussed till now, there are many more different kinds of welding techniques coming up recently, which are mostly work on these plastic and plastic material, and research is going on for joining this plastic to metal. So those things we will discuss. So mostly today, this will be on theoretical perspective. So again, as we go through, we will discuss on basic mechanisms or different kinds of techniques, and through the questions, right? Okay. So let us start. So in question one, we need to match the followings where you have different kinds of welding techniques with the mechanism of heat generation. So as I always do, let us go through different kinds of techniques as mentioned over here, step by step, and then we'll come to the question and try to figure out which one will be the correct matching, right? Now, in terms of plastic welding, if you see, what is the principle of a plastic welding? So, this is a process of joining two pieces of, let's say, thermoplastic materials at some heated state. A little amount of pressure you can apply. So basically, you are heating it up and applying pressure, because of which uh, because of which some result of cross-linking of the polymer molecules are happening over there, right? So in thermoplastic is basically made of those polymer molecules. When you are applying heat and pressure, those will be cross-linked on one another. Now here the workpieces, those are fused together with or without filler metal. You can use filler metal, you cannot use filler metal. So those things depend upon your situation, depends upon your application, how you want to join. Now, the joints which you are forming, when those parts are getting cooled below something called glass transition temperature, so we call it glass transition temperature for amorphous polymer, or if it is crystalline polymers, we define it in terms of melting temperature. So, this thing I want to mention over here, for amorphous polymer, you were mostly interested on glass transition temperature, right? And what about for crystalline polymers? For crystalline polymers, this is melting temperature. So as things happen for metals also, due to melting and solidification, here also joint forms when the parts are getting cooled below those glass transition temperature for amorphous polymers, and uh, below melting temperature for crystal polymers. Now, what is happening? So, if we try to draw some schematic, as you have gone through the video lectures also. So initially, these were all let's say this is my interface of two different polymers. So this is at t equal to, sorry, this is at t equal to 0 second, and we are not applying any kind of heating as such. So initially, these were all polymer molecule chains like this. Let's say these are my polymer molecule chains. This is my interface, right? Now, then if you are applying kind of partial heating, so not the complete amount of heating, while you are applying some kind of partial heating at the interface, they will cross link in one another, correct? So this is a t equal to 0. So it is like interfaces will confirm each other by those intermolecular diffusion. So same thing happens with different metals also in diffusion welding, right? Here also you are having this intermolecular diffusion in the sense that those molecular chains will be cross-linked into one another. And those chains can some kind of, uh, what should I say, some kind of entanglement and happen over there. Entanglement between, among molecular chains. You know? So how the interfaces will get healed? So healing of the interfaces is basically diffusion of polymer chains across the interface, and you always have to apply some kind of pressure, as I was mentioning, to improve the melt flow across the interface. You need to flow the material through one another. For that reason, you need to apply some degree of pressure over there. Now, what are different kinds of parameters upon which your degree of welding depends? So, let me remove this one. So, my degree of welding depends upon what are different kinds of parameters over there. You can have material properties, you can have temperature, you can have pressure, interface pressure, and also time. That's how diffusion works, right? It depends on your temperature, pressure, and time, right? Now, for amorphous polymers, it must be heated above the glass transition temperature. For these crystalline polymers, it must be heated above melting temperature. And yeah, so there are different kinds of processes. As mentioned over here, there are different kinds of processes for welding of these thermoplastics. So among them, what are those techniques? You already have gone through the video lectures. So what are different kinds of techniques you can use for welding of thermoplastics? Can you tell any two or three of them? What do you have? I talked about ultrasonic welding earlier for metal sheets. So initially, ultrasonic welding was developed for joining those plastic parts actually. Then thin sheets come into picture. So ultrasonic welding is one of them to join those thermoplastics. Then you have hot gas welding, then something called spin welding. Then you have vibration welding. Recently, FSW is also getting used to join those. plastic parts. There are some pros, some cons. So again, depending on your situation, how what is your plastic property, what temperature you are interested upon, what is the thickness of those plastics, how you want to mix them, what is the application actually. Depending upon all of these things, you can choose your appropriate technique to join those plastics as happen in metals also. And there is something called radio frequency welding also. No. So let us go through these techniques step by step. So what happens in hot gas welding? Let me use these spaces also. Okay. So what happens in hot gas welding? Hot gas welding, it basically utilizes heat of hot gas streams, right? So in hot gas welding, utilizes heat of hot gas streams. Correct. Now for thermoplastic, uh, you can use some kind of adhesive which can be heated until it softens, then it hardens on cooling, right? So hot gas softens up those filler material and the base material also. So if you have this base metal, let's say these are my base metals, you can use some kind of hot gas over here, and you are applying pressure from these two ends. So basically, this hot gas, as I was mentioning, that is softening your filler and base metal, and that filler is cooled or fade into the joint. So if you are using some kind of adhesive at this region, so your end product will look like something like this. So because of volume constancy, there will be this uh, kind of deformation over here. Some splashing of those adhesive due to liquefaction over there. So you are melting that, and then when you are cooling, this is getting into your solid state, right? So because of that, those polymer molecules are getting cross-linked, and when the workpiece is getting cooled, it is forming a strong joint. So that's how it works. The hot gas welding. And what are different kinds of applications of hot gas welding? You can use it in some kind of containers or some tanks for storage chemicals. Uh, then you can use it for joining tubes, some repair works. So those things are there. Now in hot plate welding, so there are two kinds of techniques as I was mentioning, hot gas and hot plate. So in hot plate welding, this is again a plastic welding process. Uh, it utilizes heat of hot plate placed between the surfaces to be joined. So you are placing a different plate which is hot in nature in between the surfaces to be joined. And then your workpieces are pressed to the plate uh, as your as your workpiece is getting into contact of that heating plate, your workpieces also are getting heated up and softened. Right? And after a predetermined time, the plate is removed, and after that, the parts are brought to the contact and placed and fused together. Same thing, just the heat source is different in hot plate welding. Again, here also the polymer molecules will be cross-linked and form some strong joint. Now, hot plates are made of which material? So, if you think of this hot plate welding, can you guess hot plates are made of which material? Some kind of thermally conductive material. So, people generally use aluminum over here. So, these are made of aluminum alloys, which are equipped with some external source of heating, which is electric heating element, and some thermocouple you can use, providing some temperature control on the plate surface, right? So, yeah. what are applications of hot plate welding? These are also again can you can use in kind of pipe welding or some automotive component welding like fuel tanks, reservoirs, batteries, those kinds of things. Now, in terms of advantages of hot plate welding, so let us think of some advantages of hot plate welding. So it can be easily automated. Here you can join large parts also. Then hot plate basically provides you confirming the joint surfaces. Hot plate provides. Hmm. Now, in terms of disadvantages, what are they? In terms of disadvantages, the welding cycle is very long over here. It's very long. So it can vary up to some 20 seconds for small parts to up to some 30 minutes for large parts. And here there will be excessive flash formation, as I was mentioning over here. Excessive flash formation. These are few of the disadvantages of hot plate welding, right? Now, hot gas welding, hot plate welding, then you have ultrasonic welding. I have already talked about the mechanism of ultrasonic welding in terms of metals. So what we do in ultrasonic welding? In ultrasonic welding, your two workpieces are bonded as a result of a pressure exerted to the weld parts combined with application of some high frequency vibration, right? If this is your horn over here, this is your anvil over here, you are joining these two surfaces. These are continuously vibrating with high frequency, low amplitude vibration that is continuously happening over the region. You know? So because of that, and you are applying some kind of pressure over there, vibration causes oscillation of the mixture and friction between those parts. So here at the interface, because of vibration, oscillation, and friction of metal surface. That is the basic mechanism happening over there. And because of that, friction of metal surface. And because of that, what is happening? Local heating is happening of that contact area, right? And when this local heating is generating over that region, the plastic melts in that contact area. Again, polymer molecules will be cross-linked and forming a strong joint, right? That is happening in ultrasonic welding. Now, can you tell me, just a minute, can you tell me different process parameters of ultrasonic welding? I have already mentioned during my metal welding courses. So, what are different process parameters in ultrasonic welding? So, you have cycle time, you have frequency of the acoustic vibration. So, those are in the range of something around 30 to 60 kilohertz. You can vary your amplitude of the vibration. Mostly people work on amplitude of some 0.05 mm. You can also use your thickness of weld part as a parameter for as a parametric study, right? And ultrasonic is mainly used for processing amorphous polymers. So like there are different kinds of amorphous polymers like polystyrene, Then you have ABS material. So can anyone tell me what is full form of ABS? So ABS is trilonitrile butadiene styrene. So mostly these amorphous polymers are generally weld using this ultrasonic welding. And again, you can use this technique in your medical equipment, in automotive components, in appliances like vacuum cleaner, dishwasher, steam iron, in your electrical equipment. Those things are there in terms of application. There are a lot of applications of ultrasonic welding. So, in ultrasonic welding, what are some advantages and disadvantages? So, in ultrasonic welding, your welding cycle time is very short. So, you can do your welding instantly, and these also can be easily automated and controllable. And here, the biggest advantage is the flash formation is very small over here, and the energy consumption is very less. So, for ultrasonic welding, flash formation and energy consumption is very less, right? And in terms of disadvantages, this is only advantages for only small and thin parts. And here you need to design your tool properly so that it can apply required amount of vibration over there, so that flash is not huge upon there, right? So this was something on ultrasonic welding. What else we have? Podcast we done. Then you have spin welding. So what is happening in spin welding? So we have spin welding. What is happening in spin welding? So in spin welding, this is similar to friction welding actually. This is similar to friction welding. So in friction welding, what we do? In friction welding, here the basically two cylindrical parts are brought in contact by a frictional pressure when one of them is rotating. So let's say this is one of your part, this is another of your part. You are pushing it, you are rotating it, and because of those friction at those interfaces, you are joining them all together. So that's how your end product will look like. Some kind of deformation is happening at the interface, right? So yeah, friction between the parts result in that heating at the interface, and after a predetermined time, the rotation stops, and because of friction, you are going up to some molten region, and when you are applying rotation, that molten region of the workpiece are fused together under an axial pressure applied until it is cooled down. So basically, initially you are heating, then going up to melting, then your rotation is stopped, and axial pressure applied from other end. है ना? So yeah, that's how it works. Now steel welding is used for manufacturing some circular parts like aerosol bottles or maybe some kind of flows. So yeah, Till now, any question? So if we are drawing some schematic of spin welding, initially we are rotating these two parts, not two parts. Initially we are rotating a single part over here, and this is blocked against the rotation in this part, right? And then you are applying pressure. It's still rotating because of friction at the interface. You are heating up material. So here the joint surface is touched due to this axial force over there. So axial pressure is applied, right? And over here your material is getting plasticized. Your material is getting plasticized and it's still rotating and you're applying pressure. And finally the friction time is terminated. You will end up with some kind of joint formation like this. It will be bulged over here because of the deformation happened, right? So this is on spin welding. We have vibration welding also. So in vibration welding, as the name suggests, here your two workpieces are vibrated at certain frequency and amplitude, right? So because of vibration, your parts are getting rubbed against each other under a pressure, causing a friction between your interfaces, which generates heat. And as you are generating heat, that is resulted in the melting of polymer in joint region. And as I was mentioning, for each of those mechanisms, when it is getting melted, the cross-linking of polymer molecules are happening, and those are fused together. And after a predetermined time, you can stop your vibration, right? Now, in vibration, so here also it's mostly similar to ultrasonic welding. Here also you can do some process parametric study in terms of you have your cycle time, welding cycle time. So in general, in vibration welding, again, this is very short in terms of some order of milliseconds. You can vary your frequency, you can vary your amplitude. So yeah, those things are there. Uh, One thing I want to mention over here that in vibration welding, you can join most of the polymers. So be it amorphous, be it semi-crystalline, be it crystalline, you can join most of them. So basically, they are produced through various fabrication methods like thermoforming, extrusion, injection molding, blow molding. Those things are there, and then they may be welded by through this vibration welding. So yeah. So for vibration welding again, what are the advantages of vibration welding? What are the advantages of vibration welding? So as you are vibrating to different parts against one another, so you can break up your oxides. Breakup of oxides is possible, right? So we call it oxidizing polymers also can be welded. And these kind of technique you can use for large and complex parts also. Then you have friction stir welding. I have already talked upon this friction stir welding in terms of metals. I've not mentioned friction stir welding in the sense of joining plastic parts as such. But yeah, you can use friction stir welding for joining of plastic materials also. So here here basically it's like a relative motion between two parts which results in frictional heating, right? So there are different kinds of friction stir welding actually. There are different kinds of friction stir welding for joining these plastic materials. One is this linear and orbital welding, and another is spin and angular welding. So these can be used most of the geometries except the circular one, right? For circular geometry, you have to use your spin or angular welding. Now, what is happening in radio frequency welding? Radio frequency welding. This is another welding technique to join those plastic parts. This is also referred as something called dielectric welding, correct? So you can refer it as dielectric welding also. So for dielectric welding, as the name suggests, your internal heat generation is happening because of some dielectric hysteresis losses in thermoplastics, right? So you're rapidly changing your electric field, and that is resulting in some intermolecular friction and heat generation over there. This is also relatively fast process and having some typical cycle time of some 1 to 5 seconds. So this is also very less, right? And again, this is used for thin sheets, mostly in the range of 0.03 mm to 1 mm. So your material must have high dielectric loss. So for dielectric welding, material should have high dielectric loss. So mostly PVC is used. Uh, yeah, mostly PVC is used. Hmm. Hmm. So this is in terms of radio frequency welding. Okay. So now coming to this, let us come to this question of matching of the following. I have already talked on this ultrasonic welding, radio frequency welding, spin welding. I have not talked about this glass welding. So what is happening during glass welding? Anyone? What is the process principle of glass welding? So your glasses will have some melting range, as I was mentioning, which is called glass transition temperature, right? So when hitting that solid glass material into that range, it will generally become softer and much more flexible. And when it crosses through those glass transition temperature, it will become a very thick, sluggish, and viscous kind of liquid. Correct? So much more viscous, it will is its surface tension will be very less. So more viscous, surface tension will be very less, right? So it will become very sticky, uh, honey-like kind of uh, uh, honey-like kind of liquefaction will be there, and So the welding can usually take place by simply pressing those two melted surface all together, and you join those two glasses, right? And the two liquids will generally mix and join at first contact. It is again some instant contact happens over there, and upon cooling through those glass transition, inward piece will solidify as a single solid piece of amorphous nature. That's how it works. Now, what are different heat sources you can use in glass welding? So, for glass welding, what are different heat sources you can use? So, you can use different heat sources like oxy acetylene gas torch flame, right? We can use some kind of furnace also. Furnace heating also can be done because the temperatures for melting glasses are often quite high actually. uh, not up to the metal, but in terms of if you compare with polymers, glass transition is much more higher than those polymer melting. So yeah, and these temperatures may vary depending on the type of glass. Like there are different kinds of glass, like lead glass. Those becomes a weldable liquid at around something like 870 degrees C for uh, what should I say, lead glass. Then you have those quartz glass, where you must be working in the range of 1650 degrees C. This is very high. So, so yeah. Now, if you think of some kind of limitations in glass welding, as glass is very brittle in its solid state, it is often prone to cracking upon heating and cooling, right? Even in metal also, when you do some alloy formation and make some intermetallics, those are brittle in nature. Here also, when you are melting, basically you are melting and solidifying the thing. You are deteriorating your base metal property. So for glass also, this is very brittle in its solid state. So here also this is prone to cracking. And this is because the brittleness of the glass doesn't allow some uneven thermal expansion. So if you're thinking of quartz, this has a very low coefficient of thermal expansion. I should mention, uh, let me mention over here. So for quartz, sorry, it is having very low coefficient of thermal expansion, while something called soda lime glass, which is having high coefficient of thermal expansion. So it is usually important to closely match their coefficient of thermal expansion so as to ensure that cracking doesn't occur, right? Now, welded glass needs to be cooled very slowly and evenly through the glass transition temperature. What that process is called? If the cooling rate is very slow in heat treatment, what is that process called when your cooling rate is very slow? Near, so you're doing some annealing heat treatment. No. So your welded glass that needs to be cooled very slowly and evenly through that glass transition temperature. So you're basically doing some kind of annealing treatment to relieve any kind of internal stresses form over there created by a temperature gradient. Correct? Hmm. Now can you tell me those can you match those followings and give me a correct answer? So you have ultrasonic welding, you have radio frequency, glass and steam. So for ultrasonic welding, what is the mechanism? It's vibration create local heating, right? For radio frequency, It's dielectric hysteresis loss. For glass welding, as I was mentioning, you can use the gas torch or you can use those furnace heating over there. And for spin welding, this is mostly similar to this frictional heating. All agreed? So my ultrasonic welding is D, radio frequency welding is C, glass welding is A, and frictional heating is for spin welding. Option C. Yes, Chintu. So option C is correct. Okay. Now in my question two, we need to fill up those blanks over there. So I have already talked about this glass welding process. So it says in the glass welding process occurs. I don't know. Uh, Let me know which one it will be. Welding process occurs above or within or below the glass transition range, and once the fusion of parts complete, they are pulled very fast or slowly to relieve or maintain the internal stresses generated by the temperature gradient. This is very simple question. Which one should be the correct answer?
Sir, above and very slowly.
Hmm.
First one is above, and second one is very slowly.
Above very slowly and to relieve the internal stresses, right?
Yes.
Okay. So this I have already talked about. This is above. So you need to melt the material over there above the glass transition temperature, and you're fusing them and then cooling it. And that cooling should happen very slowly, otherwise it will form those brittle. So there is something called brittle transition. So you're forming if you are doing very fast cooling, even in your metal parts, you are if you think of this uh, iron carbon TTT diagram, there is those martensite formation, which is again very brittle in nature, and you are doing it slowly and evenly to relieve. Sorry, to relieve the internal stresses generated during a temperature gradient by the temperature gradient. Okay, here you need to choose the correct welding process among the following that can be used to weld ceramics. So this is something on ceramic welding. So till now we have not talked regarding ceramic welding. So yeah, in terms of ceramic welding, ceramics have ceramic have the highest potential because of their increased toughness, high heat resistance capability, and some non-catastrophic fracture behavior, right? So if you're thinking of in terms of uh, yeah, we can use this space. So if you're thinking of in terms of strength to weight ratio, strength to weight ratio, and operating temperature, where your ceramic stands over there. So let's say this is the region where my conventional materials work. Conventional materials in the sense the high temperature material, the pure metals. So you have titanium or some super alloys. So you have Hastelloy, nickel-based alloys, titanium, those things are there. And then your operating temperature. So you have this. You can have this metal matrix composite over there. Metal matrix composite in the sense, what is a metal matrix composite? So you're mixing some kind of ceramic materials into your metal matrix. So you're mixing them all together and form some much more tougher, much more harder material. So the applications of those metal matrix composite, let's not go into that detail. And then if you have metal matrix composite over here, ceramic stands somewhere nearby those metal matrix composite in terms of operating temperature range and strength to weight ratio. And finally, the strength to weight ratio is much higher for the ceramic composite. So your ceramic composite somewhere stands over here. And finally, you have this carbon composites. So you can use this carbon fiber, right? Carbon composites, it can stand somewhere here. So this is having the highest strength to weight ratio with highest operating temperature range. Those are uh, carbon fiber composites. Now, what are different processes to weld ceramics? You can use electron beam welding. I'm not going into again the process mechanisms of electron beam welding, laser beam welding. Those things I've already discussed. Uh, Diffusion welding also you can use to join ceramic materials. Now, basically, your high beam energy that is restricted to small ceramic parts. That is, it can be used only for ceramics with different melting points. Like what are different kinds of ceramics you have? You can think of Al2O3, which is having some defined melting points. So high beam energy that is restricted to small ceramic parts. And then when you are when you are processing any kind of ceramic material, high stresses can be caused by severe temperature gradient, and that can easily damage ceramic joint actually. So for ceramic joining, high stresses caused by severe temperature gradient because of its low thermal conductivity of ceramic, and that can easily damage ceramic joints actually. Now, ceramics can be joined to themselves or to metals, as I was mentioning by diffusion welding also, and it is complicated to apply the necessary pressure for larger components, right? And in terms of economical joining process, you can do some kind of brazing for ceramics. So both metallic and ceramic brazes are available to join ceramic materials. Now, as I was mentioning, what are properties of a ceramic material? You have high temperature resistance, you have extremely high hardness, your electrical conductivity will be low, uh, your thermal insulation property will be high, right? So those things are there. Yeah, not going to application, but there are a lot of applications again. So in aerospace technology, metals are unsuitable for the hot structure of due to their poor behavior at high temperatures, right? The conventional metals and their high density also, and that problem is caused by their high coefficient of thermal expansion. So over there you can use those ceramic materials, and for ceramics, inherent high temperature limits of metal are also uh, it's kind of handicapping other major technologies. Now, we can think of some limitations also for welding of ceramics, like it is difficult to process, and basically some it is difficult to process, and small resistance to thermal shock is over there. So since ceramic material is porous also, so porosity tend to be produced in the weld bit always. And when you join the ceramic materials, you can see lot of round small pores which are not connected with each other, and uh, those those can be found along the fusion boundary, right? And because of the relatively small thermal conductivity of ceramic materials compared with the high thermal expansion which is there, so your ceramic materials is having low thermal conductivity, high coefficient of thermal expansion. So stresses in the material can occur leading to its destruction. है ना? Okay. So where were we? Choose the correct welding process among the following that can be used to weld ceramics. Can you mention the correct one? So you have ultrasonic, spin, diffusion, radio frequency, laser, and friction. Which one should be the correct answer? Can we use ultrasonic welding for ceramics? No. Can we use spin welding for ceramics? No. Diffusion welding is one option, and laser beam welding and friction welding. I already mentioned, right? So these three techniques you can use over here to join ceramic furnace. Any question till now? Okay. What my next question asks? You have to identify your true and false statement. The first statement is something on laser transmission welding. Okay, we will discuss on laser transmission welding then. Then there are some statements on glass welding which I have already talked on, and something on metal to ceramic joining. Okay, so there is this laser transmission welding, and then metal to plastic joining. We will go through one by one. So what happens during laser transmission welding? Let us draw some schematic over here. So you have two materials. Two materials. So XCD is wrong. Not two materials. one below another. So one is transparent to infrared laser. What about the other? This is the absorbing material, right? And you apply some amount of clamping pressure. So you are applying clamping pressure over that region, and your laser beam is generating some heat at the interface. So transmission welding, or laser transmission welding, or laser plastic welding, or you can say through transmission welding. The basic principle is transmitting your laser radiation through one piece of plastic, which is this one, which is transparent to the to the infrared laser to create that weld. So transmission welding aims to apply the energy in between two plastic pieces at their interface, right? Their upper part is transmissive, the upper layer that needs to be transparent uh, to some specific laser wavelength uh, in the range of, let's say, from 800 to 1000 nanometer. So that is transparent in that laser wavelength in the infrared or some near infrared spectrum. So that is my upper part. The lower layer must be absorbing. Otherwise your heat will not be generated at the interface, right? So what is happening at the lower layer? Your lower needs to have that ability to absorb the light energy to create heat. So most commonly and the best absorbing additive is you can use carbon black, which you can dope at some specific rate. So that's how we make some material as absorbing material. And the next parameter is your clamping or contact pressure, right? Otherwise, basically your thermal energy must be transferred from that upper layer to allow for it to soften and melt, right? So for that reason, you have to have some kind of consistent contact clamping force required over there. So yeah, in terms of process requirement, uh, the plastics to be joined that require similar chemical compatibility, and those plastics needs to have some similar melting and softening ranges also. So both plastics will be melting at or near the same time. So this is my process requirement for laser transmission welding. One is this material compatibility. So here you have to have this similar chemical compatibility, and similar melting or softening range. है ना? Hmm. So in terms of materials, what you can use polypropylene, you can use polycarbonate, you can use ABS polymers, you can use polystyrene. So those materials are there. You can use nylon also, right? So in terms of advantages of laser transmission welding, again, in terms of advantages, You will have minimal mechanical stress and not applying any kind of external load over there. So you have minimal mechanical stress as you are relying on laser transmission. The energy control is precise. Then you have uh, so in terms of some secondary advantages, you can have minimal flash formation and minimal particulate development. So it's kind of clean, consistent welds down to the micrometer range. And also cycle time is very high. Uh, High in the sense this is very fast process. Cycle time is cycle time is low. It's fast process. So these are some of the advantages of laser transmission welding. Okay. So then can you tell me what will be means which statements are true, which statements are false? The first statement says the transparent upper part is required for the laser transmission welding process. This is true, right? Agreed? Yes or no?
Yes, sir. I think, sir,
Agreed.
option B is correct.
Huh?
Option B is correct. Option B.
Option B. Okay. This is true. The lead glass needs to be heated at a higher temperature. Yes, this is false. The vice versa is true. Then welding of ceramic can be done most, yeah, as this also I mentioned. This is also true. And thermoplastic matrix composite can be joined by resistance. Yes, okay. So I've not talked about this metal to plastic welding, right? So that also need to be covered up. Though I'll come to that a little bit later. Let's discuss more on this question, but then we'll move to that plastic to metal welding process. So, okay, this is again something on plastic to metal. ठीक है, let us discuss on that plastic to metal welding. So, what we'll discuss on plastic to metal welding. Just wait for some time. So, we are discussing on this plastic to metal welding. So, basically, demand on those dissimilar material joining this is increasing now, and yeah, from the viewpoint of design requirements, energy consumption, environmental concerns, because of all those things, both in terms of metals, so you can think of dissimilar metals. So maybe if you're, I don't know, you know this busbar term or not. So in electric vehicle, there is something called busbar. So which basically is a current carrying material which distributes your current. So there, the most electrical conductive material you can think of, copper. Again, the copper is very heavy, very costly. So next easily available material and lightweight material you can think of is aluminum. But aluminum have certain disadvantages, like it can oxidize very easily. So whenever you have joint, it can oxidize, it can increase your temperature, and so basically there is a possibility to catch a fire in your battery, right? So people are uh, people are demanding more on hybrid kind of hybrid kind of end product. Like if you can somehow uh, think of in terms of bimetallic busbar made of both copper and aluminum. So when where there is this connection is happening, you make it of copper, and the middle part where the current is flowing. Once there is copper in the connection in the busbar, so you can basically eliminate those disadvantages where the aluminum was carrying. And again, if you are making it both made of copper and aluminum, this is more beneficial in terms of economy, in terms of current carrying capacity. So everything will be taken care of. So yeah, in terms of this design requirement and energy consumption, this dissimilar material joining is coming into picture very rapidly. So in terms of plastic to metal welding, so if you are thinking of metals, those are usually have been selected since they have superior properties such as high ductility, high thermal conductivity, high machinability. Meanwhile, for plastics, what advantages they offer? So plastics are having excellent corrosion resistance. Uh, they can be lightweight material. Some insulation property can be done through plastics. So dissimilar material joint between polymer and metal can be obtained from both of the two different properties at the same time, right? Now, how those technical difficulties arise? Due to dissimilarities in mechanical, thermal, chemical behavior. So, as you're thinking of aluminum and copper in terms of dissimilar metals, there also you have this different mechanical, different melting temperature, different chemical affinity, different thermal range of basically working temperature is completely different for aluminum and copper, and same can be said for plastic and metal components, right? Now, for example, if you think of some example, so let us think of some polymer material which already professor had given as an example. So there is something called PET material, polyethylene terephthalate. Okay, and let's say we are comparing it with stainless steel. So in terms of melting point, what is the range of PET polymer? It's somewhere around 200 to 250 degrees C. For SS, this is huge. The temperature difference is huge. In terms of thermal conductivity, what is thermal conductivity of some kind of polymer? This is very less. The thermal conductivity for a polymer is very less. Whereas for SS, this is somewhere in the range of 150, the thermal conductivity. Now, in terms of coefficient of thermal expansion, in terms of thermal expansion coefficient, So 10 to the power minus 5 per degree C. This is somewhere around 5 to 7. And this were somewhere around 2. So here also you have this, here also you have this dissimilarities in terms of different material properties, right? Now, polymer metal hybrid joints are formed using various joining techniques such as normally people use this adhesive glues or some kind of mechanical tools such as bolting or riveting, like those kind of things are already available in market. So use of adhesive bonding for joining aluminum and this there is some polymer called polytetrafluoroethylene PTFE that is successfully achieved only after treating this. So obviously research have been done and it's still going on in terms of plastic to metal components. So in terms of this polytetrafluoroethylene to aluminum joining, people have done that joining through some reaction with sodium, and then they have somehow figured out that it works when the adhesive is reacting with sodium, and then you can get some successful joint over there. Now bolted joints of this carbon fiber reinforced epoxy and titanium. So that is another research domain. So there the bolted joints that results in an increase in joint strength, but some drawbacks such as you can you will have this long processing time, it will have some high production cost, some limitation of shape and size. Those are identified over there. Yeah. Now, obviously, there will be some disadvantages of this thing, this adhesives and bolting and riveting thing. So, adhesive bonds for joining, those are problems in terms of environmental restrictions on the emission of volatile organic compounds, and yeah, those are difficulties of mass production. For that reason, people are now coming to joining the two components. So, you want a permanent joint over there. For that reason, you are having this laser beam welding, resistance welding, those are used to join those plastic to metal parts, right? Now, yeah, yeah. In terms of this mechanical fashioning, like bolting and riveting, so those are either too intrusive, like stress concentration will occur over there, right? Those stress concentration resulting from if you are making some hole or drilling the component to make some bolting or riveting over there, right? And because of that, stress concentration arises at that region, and that require extensive surface preparation, which are incompatible with mass production requirement always. Alternatively, what we are doing, well, fusion joining. So your fusion joining methods, and particularly this, as uh, as mentioned over here, resistance welding is mostly used when applied to this thermoplastic matrix composite. Those have been proven to produce those close to parent strength joint. So it's close to the base metal strength that can be uh, that can be occurred in short processing time. So this is a very highly reliable welding technique. This resistance spot welding for thin metal sheets to plastic component. Now you will have this laser welding also. So in terms of laser welding, you have the advantages of this precision manufacturing or material processing on small parts or geometries. Then it can be focused into very small size, which is useful for joining complex shape and micro parts. And also this is a non-contact process. This is the biggest advantage of laser, right? Now in laser, in laser welding, there is something called beam offset, which will obviously have some effect on your welding product, on your welding end product. So Yeah, yeah. So here actually, I've talked a lot. Um, Here I have some space. So let us discuss something on this effect of beam offset. What is the effect of beam offset? So laser joining can be applied by laser irradiation from the polymer side. So laser transmission joining has happened as I was mentioning, or from the metal side. So when it is coming from the metal side, that is called conduction joining. When it is coming from, this is called conduction joining. When the radiation is coming from polymer side, this is called laser transmission joining, right? So that is basically giving more flexibility for joining options under different settings, right? Now, how will your joint strength and your bead width will increase as a function of temperature? So that will increase as a function of increasing thermal input, right? So further increase in thermal input value that causes some polymer degradation, extrusion, bubble formation, explosion. So you have to optimize your process parameter in such a way you get some good bit of joint strength. This is in terms of laser transmission when irradiation is coming from the polymer side. Now, when you are thinking of in terms of conduction joining, for that case, the joint strength and beat width again increases as a function of with increasing thermal input. But further increase in the thermal input that causes a decrease in the strength, right? You should not have much melting over there, and uh, whenever you are doing some melting, you are degrading your material property. So there must have some optimization which need to be taken care of. Hmm. Where were we? Question 5. Yeah. So yeah, in terms of discussion, first we have covered up all the welding techniques a little bit, the basic principles. ठीक है. So what will be the answer for question 5? Which of the following process cannot be used to join metal to plastic? Oh, there is one thing I have skipped. Ultra short pulse laser welding. Okay. Just tell me the answer for question 5. Then we'll discuss on something on ultra short pulse laser welding. Cannot be used. Laser beam welding can use, resistance welding can use. So option D is correct. Uh, uh, Cannot be used. So I cannot use my radio frequency welding as I had mentioned. And there is something called ultra short pulse laser welding. So what happens in ultra short pulse laser welding? Let me look this up. So as the name suggests, in ultra short pulses, the laser will emit ultra short pulses of light, generally of the order of some femtoseconds to some picoseconds, 10 picoseconds. That is the order of pulses, right? And it will be extremely high powers in ultra short pulses that can be achieved through some YAG laser. We call it YD YAG laser. Through this laser, extremely high power can be generated in ultra short pulse. Now, time of heat transfer is extremely small over here, right? You are providing very little amount of time for the heat transfer in the material. So your heat affected area in that sense will be very small. That is the biggest advantage of your ultra short pulse laser welding. So as I was mentioning, the USP lasers, they emit laser pulses with extremely short pulse duration, typically in the range of 10 femtosecond to 10 picosecond. The power density is very high over here. So my advantages are extremely small, not small, extremely short, extremely short pulse duration, very high peak power density. What are the process parameters over here? You have the cycle time, you have the energy per pulse, you have the, as this is a USP laser, as you are providing pulse, so some parameter can be pulse repetition frequency and your power, average power of the laser. Those are some of the process parameters, right? Now, in terms of process principle, so laser energy of this femtosecond pulses absorbed by the nonlinear process that is utilized as a heat source for Gaussian welding, mainly for glass material. So extremely short pulse duration allows this nonlinear absorption process, which differs from conventional absorption process, right? So if you're having this extremely short pulse, the complete process will be nonlinear in nature, and that will be leading to a non-equilibrium state in the process region. So your process will never be in equilibrium state. You are not giving enough time to equilibrate, right? So your linear absorption always requires an opaque material, some kind of opaque material to absorb the heat up. But nonlinear absorption occurs even in transparent materials at very high energy densities. That's how nonlinearity happens, right? So due to nonlinear absorption process, the laser pulse energy is deposited solely in the focal region. So it is a nonlinear absorption process. Pulse energy is deposited solely in the focal region only. Correct? Now, laser focus is placed at the interface. So the combined action of nonlinear absorption process and heat accumulation is happening. So because of the combined action of these two, that leads to the welding of the samples. So if the time between the successive pulses is shorter than the time required for heat diffusion, out of the focal volume of heat accumulation occurs, and that leads to some stepwise increase of the temperature. So my time between successive pulse is shorter than the time required for diffusion. What will happen? So out of focal volume heat generation, out of focal volume of heat accumulation happens. That leads to a stepwise increase in your temperature. So your glass material that can be locally in a molten state and then resolidify, right? Now, as here the cooling rate is much faster because you are going up to so high power power density. As your cooling rate is much faster, the solidified glass exhibits some higher fictive temperature. So fictive temperature defines your structure of a glass. So I'm also that not much that experienced in this glass material as such. Anyhow, so this defines your structure of the glass because of your higher cooling rate, right? Now you can do some seam welding by moving your laser focus. You can do some continuous welding seams, right? You can do in continuous laser welding also. And then if the laser focus is located at the interface of two samples, uh, basically you are melting and then resolidifying of your molten material that forms these strong bonds between those samples. Now, in terms of advantages of USP laser, what is there? So here you do not have any kind of annealing step, right? I had mentioned that you have to do some kind of even cooling and slow cooling, but because of these ultra short pulses, here there is no need of annealing step as such, which requires to strengthen the bond material. So in the process mechanism itself, in such a way that you can end up with some good amount of strengthening of the bonds with it can be done with widely different thermal expansion coefficient. And in USP laser, there is no thermal or shock wave damage, right? As compared to longer pulse duration and high peak power laser, there is no thermal or shock wave generated in the USP laser. And of course, your heat affected zone will be very small. And because heat affected zone is very small, the induced thermal stress will be minimized. Those things are there, right? Okay, so here we talked about this ultra short pulse. What about question 6? The friction welding process is similar to which welding process in terms of heat generation? Is this radio frequency? No. Red laser beam? No. It's a spin welding. So here my option C is correct. Right? Any question? Sorry. Okay. Then we need to fill in the blanks basically for ultra short pulse laser welding. So ultra short pulse laser welding process uses this ultra short pulses of whatever is this power light for dash period of time to join parts. As a result, heat affected area is also dash. Which one will be the correct one? So in ultra short pulse laser welding, the power density is extremely high. You know, as I mentioned, because you are working on some femtosecond to picosecond order, the power density is extremely high for extremely short period of time. And your heat affected zone, because of as a result, the heat affected zone will be very less, right? Now, which of the following statements are correct for laser transmission welding? It says that laser is aimed at the interface of two plastic pieces. Then it says lower surface should be of absorbing nature of the light to create heat. Any type of plastics can be joined irrespective of its chemical compatibility, and clamping force is not required. Which one is correct?
Sir, sir, first and second are correct. One
First
and
and
two.
second and correct. Exactly. So option C. So my laser is aimed at the interface of two plastic pieces. Yes. And as I mentioned, that time lower surface should be absorbing to create the heat at the interface, and the upper part should be transmission. So here my option C is correct. Can you tell me the correct one for question 9? Which phenomena are involved in the thermoplastic welding process? It's cross-linking of the polymer molecules. As simple as that. So, any question? Is there any question?
No, sir.
Okay. Shivam, you want to ask anything? Okay. So move to the final one. Which of the following welding technique is also referred to as dielectric welding? Is also already talked about radio frequency welding, right? Yeah. So today's session was very much on theoretical aspects actually, uh, in terms of different welding techniques for joining those ceramics or plastics. So excluding from the metal parts. Okay, so if you do not have any question, we will finish it over here.
Sir, can I ask a question?
Mhm.
Sir, please, can you please explain the different kinds of plastics, like thermoplastics, thermo settings? What is the difference among them?
Mhm. So your question is, what is the difference between thermoplastic versus thermosetting plastic, right? Thermoplastic and thermoplastic polymer and thermosetting polymer. No?
Yes, sir. Yes, sir.
So actually, these two sound very similar. So, but they're totally different compounds actually, and they basically have different properties as well in terms of applications also. So, talking about the differences between thermoplastic and thermosetting plastic, the main distinguishing factor between the two is that um, thermoplastic materials typically have low melting points. So thermoplastic materials typically have low melting points, due to which they can further be remolded or recycled very easily. On the other hand, what happens for thermosetting plastic, this is quite opposite in terms of this melting temperature. So they can withstand the high temperature, and once it is hardened, this cannot be reformed or recycled even with the application of heat. So in any case, uh, this is the major distinguishing factor. So there are other differences also, like mm, thermoplastic can be synthesized by some additional polymerization, and there is something called condensation polymerization. Let's not go into that bit. So if you're talking about how can you basic differentiation between thermoplastic and thermosetting, it's all about this melting range of these two materials. One can be recycled, one cannot. And also, yeah, thermoplastics are low tensile strength compared to thermosetting, uh, because thermoplastics are lower in molecular weight compared to thermosetting. So molecular weight also less for thermoplastic materials. That's why the tensile strength is also less.
Sir, this glass transition temperature, it is applicable to thermoplastics only.
Not really. So every polymer material need to be cured after melting. So glass transition temperature, thermoset also can have some glass transition temperature. But the melting range will be higher than the thermoplastics.
Yes, sir. Thank you.
Okay. Thank you. Okay. Bye bye.
Bye, sir.